Hello, welcome everybody. My name's James Page. I'm a technical architect. I work for Canonical on the Ubuntu OpenStack engineering team. Been with Canonical for about 7 years, working pretty much on OpenStack for that entire period, so I do remember the very early releases and some of the pain points there. I spent about 20 years working with open source technology in enterprise environments. I'm, among other things, a Debian developer, Ubuntu core developer, contributor to the Novel LXD driver, which I'm going to be talking about today, and I'm the current PTL of the OpenStack Charms project, which is a set of deployment tooling for deploying OpenStack. Now, I appreciate I stand between you and lunch, so I'll try and keep it to the 20 minutes we've got left, but if we run over a bit, we can always do questions outside over something to eat. Okay, so quick show of hands. Who's heard of LXD to start off with? And I'm assuming everybody's heard of Ceph. Yeah, good, excellent. So, and everybody's heard of OpenStack, so that's cool. So, let's start off with a bit of a deep dive on LXD and what it is and what it isn't, and how it fits into the overall ecosystem of container technologies and full hypervisor virtual machine technologies. So, probably all familiar with technologies such as Docker and Docker. These are very much geared around providing containerization of single processes in an immutable deployment topology. So the idea is that you throw away your container and provision a new version of it rather than running any upgrade process within it. They're typically used in container orchestration solutions such as Kubernetes, and that's not where LXD fits. LXD is about full machine containers, which I'll talk about in a little bit more detail in a second. We've then got virtualization technologies such as VMware ESX, Hyper-V, and KVM, which provide full virtualized virtual machines with kernel, firmware, virtualized network interfaces, block devices, CPU, memory, etc., etc. Now, LXD fits in alongside these technologies, and it's providing a full system container. That's a container that contains everything from init onwards, but it doesn't require a separate dedicated kernel or firmware like a full KVM virtual machine does. That does in itself bring one limitation, and the only thing you can put in a LXD container at the moment is a Linux operating system. So that could be Ubuntu, it could be CentOS, could be RHEL, mainly because it's sharing the kernel with the host operating system rather than having a dedicated one. So don't try and boot Windows in it, it doesn't work. So in terms of LXD itself, who's heard of LXC or LXC? Okay, so LXD builds on top of LXC. It's not a fork. It uses all the same libraries and Linux kernel technologies under the hood and leverages all the investment and IP that's been made in Linux containers generally over the last probably 8 to 10 years, I guess, since IBM initially started that work. It's designed as a daemon that runs on top of LXC. It provides a REST API, and it provides a set of management functions which are more hypervisory or similar to what libvirt provides for KVM on top of LXC itself. It's designed to be simple, very simple API to interact with, very REST-oriented, network accessible or local Unix socket accessible. LXD was designed to be fast from the ground up. So it leverages a lot of other Linux technologies in addition to containers. Presume everybody's heard of ZFS. Okay, so one of the storage backend options, and the preferred one, in fact, is to use ZFS for the root file systems for your LXD containers, and that provides us with a number of options in terms of using things like copy-on-write clones, so we can very quickly spin up a LXD container from a gold copy image and get very, very high density onto a single LXD host. LXD was designed to be secure by default. Anybody remember the early days of LXC where everything ran as root and you couldn't trust anything? Yeah, it was pretty bad. But the Linux kernel's come a long way with user namespaces, both for networking and processes now. So LXD provides unprivileged containers by default. So although when you log into a LXD container, you'll see things running as root, actually on the host, they're not running as root. They're running as a subset of user IDs and group IDs from the actual accounts that are running on the configured on the host that's providing the LXD services. So if you, God forbid, there was a kernel security vulnerability or LXD vulnerability that allowed a breakout from a LXD container, that breakout is only going to run as an unprivileged user on the host itself. We also provide additional sandboxing through use of AppArmor and SecComp, so that the process group for a particular container is only allowed to access the parts of the system that it's been allocated, so that whether that be network interfaces, ZFS volumes, log files, whatever it is, there's an additional sandboxing around that. So secure by default was a key design objective for LXD. And as I said, it provides hypervisor-like features, so snapshotting of containers, creating images from those snapshots, migration of containers between different LXD hosts. These are all features that were baked into LXD from the ground up, which gives you a very nice end-user experience if you're using this either on a laptop or on a large server. So taking into account all those features, let's take a look at how we've integrated LXD with OpenStack. So, as we know, KVM provides the capability to host multiple guest virtual machines on a single host with the fully virtualized BIOS, firmware, kernel, CPUs, networking, and storage. LXD provides us with a very similar capability. We're hosting multiple full system containers on a single host, providing the same similar virtual machine concepts, such as memory and CPU resource controls, networking, and storage. So as these two stacks provide similar concepts, LXD and KVM both map naturally into the machine model and machine storage and networking model that OpenStack clouds present to end users. As a result, the Nova LXD driver supports operations that any user of an OpenStack cloud should be familiar with. This includes the regular instance lifecycle operations, but also some operations that have been traditionally hard to do with containers in the past, such as creating image snapshots, hot plugging network interfaces, and into running containers, do migration between hosts. That's all supported as part of the Nova LXD integration. As LXD containers are managed as full system containers, they're fully accessible via SSH. They use Cloud Init on boot, so you can specialize them on first boot exactly the same way as you would do a traditional KVM image. And all your existing deployment and management tooling should be able to make easy use of containers within an OpenStack cloud. Like I said, we can also migrate containers between hypervisors. Currently, the 100% best way to do that is with them turned off. There's still work ongoing in the Creo stack to do live migration of containers between hosts. It works in some use cases, doesn't work in all use cases yet. That's still a development area for LXD and the Linux kernel itself. The driver also applies the properties associated with the flavors you're using into the containers. So if you specify 2 CPUs and 2 gig of memory, you're going to get those applied to the container. So if you log into the container, that's all the memory you're going to be able to see and use for the applications you're running in it. We also support some other finer grain controls, so things like ephemeral disk capacity for your root volume, your swap device, and any additional ephemeral storage being provided by the local host. You can have disk quotas put on it based on what's provided by the flavor, and we provide some more fine grain control over things like disk IOPS to those block devices. In terms of networking support, we have full support for both the Linux Bridge and OVS drivers that are part of the Neutron ML2 plugin. For firewalling, we support both hybrid and native firewall options in Open vSwitch, so that gives you the full suite of either using overlay networks for your LXD containers, potentially alongside KVM containers, or plugging into underlying provider networks, either via VLAN or flat networking. So something we've been using quite a lot in deployments that we do with Nova LXD is the concept of taking an entire hypervisor node and providing a single container on that for exclusive use, which we've been calling exclusive machine containers. It's not particularly catchy, but it gets the message across. So by providing a full machine with a very thin, lightweight container on it, we basically give someone an entire server to use without the additional complexity, operational complexities that giving someone a full bare metal machine with full root access via the kernel into firmware and BIOS and all the other various things that can be used for wrapping that in a LXD container, we provide an additional security wrap, but allow a potentially untrusted tenant of a cloud to access the whole machine in terms of the resources that they can use. That by using a LXD container there, we also get quite a lot of flexibility in terms of plugging into whatever SDN choice is being made for the OpenStack deployment. So we can plug it into overlay networks because we've got a very small hypervisor LXD wrapper around the container. And we can also plug it into whatever block storage you're providing as part of the cloud, which brings me on to a new feature for the OpenStack Pike release, which is out in the last month. And this has been a gap in the Nova LXD driver for the last 12 months or so, but we now support presentation of Ceph Rados block devices via Cinder to LXD instances. So the Nova LXD driver has been useful for where you've got ephemeral instances that you don't need to attach any large block storage to in the past, but now you can also use it for where you need persistent block storage capability for things like databases, that sort of stuff. It's been implemented using the native RBD support in the Linux kernel to present block devices directly into LXD containers, and that's all integrated via the OS Brick block device mapping library that both the libvirt driver and the LXD driver use for managing block device mapping into virtual machines and containers. Right now, you can only use ext4 on those block devices. This is a limitation in the Linux kernel, and that's the only file system that has support for user namespacing, so it can be consumed from an unprivileged container. I'm sure other file system types will come along in the future, but that's a limitation at this point in time on using those block devices. Now, if you want to try this feature on Ubuntu 16.04, the recommendation is that you use one of what we call the hardware enablement kernels. So this is a backport of a newer kernel version back to 16.04. The specific purpose of those is actually for hardware enablement for new server hardware, but you also get all of the new features of that kernel. And the 4.10 or 4.11 kernels have much better support for newer Ceph releases, including Joule and the latest Luminous release, which forms part of the Pike OpenStack release for Ubuntu as part of the Cloud Archive. So if you want to try out this feature, that's the recommendation there in terms of having the right level of RBD support in the kernel to support the Ceph backends that you're going to be using. So all in all, that means that using Nova LXD in a cloud is very much like using KVM in a cloud. You should be able to lift and shift the majority of your workloads from KVM to LXD with minimal tooling changes to achieve that type of migration. But I guess the question is, why would you want to do that? What's a machine container giving you that's so much better than a KVM container? Well, we talked about the fact that there's no additional kernel, no additional firmware. The cost, all the processes in a container are on the host kernel, so it can be load balanced across the available CPUs. There's no kernel context shifting as the QEMU processes go on and off CPU. But what does that actually look like from a performance perspective? So I'm going to go through 4 sets of performance figures. These are all done on commodity Dell hardware, which is actually remarkably old now, but was a good benchmark for the figures we wanted to see. And we did benchmarking directly on hardware, so that was with no OpenStack involved at all. Benchmarking using OpenStack with the LXD driver, and benchmarking using OpenStack with the libvirt KVM stack. For the 2 OpenStack use cases, we used Open vSwitch networking with VXLAN overlays. So, who's heard of Spark? Okay, not many big data people in the room, but this graph shows the total time taken now to complete a Spark model for spatial and geographical analysis of credit card spending for fraud detection. So the shorter the bar, the better here, because that's the shorter amount of time it took to compile the model for use. So if we look at the bare metal and LXD figure, Nova LXD took about 10% longer than running directly on the bare metal. We looked at this, and we think this is actually due to the networking overhead of using overlay networks compared to the bare metal workload that was directly on the underlying network fabric and using jumbo frames. So there was a network throughput and latency difference there, which we think accounts for the 10%. But if we look at that compared to KVM, the same job took nearly twice as long to complete. So we've got same amount of compute resources available to each instance, the same underlying network technologies, but the cost of context switching and virtualizing all I/O is expensive in terms of this type of workload. And I'm seeing everybody's had a TerraSort, it's a popular Hadoop benchmark, which basically takes a large set of randomly generated data and sorts it into order using Hadoop MapReduce tasks. It's a great benchmark because it exercises memory, CPU and block, and network device I/O. It is slightly skewed towards sequential read and write, but it does give you a bit of a flavor as to what the performance of a particular hardware or virtualized architecture looks like. Again, you can see that the hardware and LXD figures are very, very close, and this really does reflect the very lightweight way that LXD is compartmentalized, is slicing up the hardware for use. KVM was significantly slow here, and we actually had using exactly the same configuration across all 3 deployments for Hadoop. We had a number of the MapReduce tasks need to be retried because they failed during execution. We tried this multiple times and we got the same result every time, but ultimately it resulted in the TerraSort completing, but taking a lot longer to complete for KVM compared to the other 2. Again, we had the same network overhead, about 10% difference between LXD and bare metal itself. Okay, so both of those workloads are quite sequential read-write heavy in terms of disk and network I/O. So we've also done some benchmarking around much lower latency small network ops, which are much more random in terms of the patterns they put on network activity and block device activity. Everybody had a Cassandra, it's a distributed database solution, and we used the Cassandra stress benchmark, which basically creates lots and lots of writers with lots and lots of small network ops and runs that against the Cassandra deployment. So it's quite a different I/O profile when compared to Hadoop. So we looked at the latency figure here. So latency for any write operation during the stress was on average about 30 milliseconds for LXD and about 100 milliseconds for KVM, which had a direct impact on the overall throughput of the test as well. So we could get 15 to 16,000 rows a second out of the equivalent hardware for LXD, but we're seeing around 3,000 to 4,000 rows per second for the same hardware being virtualized using KVM. And this is really to do with the cost of virtualizing all the network I/O and disk I/O operations and the cost of switching the virtual machine on and off CPU in KVM compared to those processes just running directly on the host kernel that we have with LXD. Okay, so we've got about 5 minutes left in the run-up to 1 o'clock and lunch. So if anyone's got any questions, I'm happy to answer them now or at lunch, but the question is LXD NUMA-aware? LXD itself is not. We have some initial design on how we would use the Nova LXD driver to inspect the NUMA topology of a particular machine, and then use LXD profiles to make sure that a particular container was only ever scheduled onto a particular part of the NUMA topology of a system, but that's not a feature that's currently supported. I envisage that the consumption model for that would be very similar to how you would do that for a libvirt KVM machine in terms of adding some additional properties to a flavor to specify either isolation or NUMA topology mapping properties, but not yet. But the potential is there to do it, definitely. Any other questions? Okay. Well, thanks very much for your time. Everything I've talked about today is free, open source, so there's nothing behind a pay firewall or anything. The Nova LXD project is upstream under OpenStack. We're not in tree with Nova yet. We're still an out-of-tree driver. But if you want to try us out and give us some feedback, it'd be much appreciated. Thank you.